Could we prevent it? After witnessing the catastrophic aftermath of an asteroid impact, a question naturally arises. Could we actually prevent such a disaster? The answer depends on two critical factors: how much warning time we have and how effectively we can deploy our limited planetary defense technologies. Our current detection capabilities form the foundation of any prevention strategy. NASA's Jet Propulsion Laboratory operates the Asteroid Watch program, which tracks near-Earth objects that might pose a threat. As of late 2022, this program had successfully identified about 90% of near-Earth asteroids larger than half a mile wide. The good news is that none of these known large asteroids shows a significant chance of hitting Earth in the foreseeable future. However, detection represents only half the equation. Can we effectively change an asteroid's course once we find it? This is where significant technological gaps exist. With years or decades of warning, several promising deflection methods become viable. With only months of warning, our options narrow dramatically. And with just days or hours, as in our hypothetical scenario, prevention becomes nearly impossible with current technology. The most thoroughly tested deflection method is the kinetic impactor approach. This technique involves deliberately crashing a spacecraft into an asteroid to alter its trajectory through momentum transfer. In 2022, NASA's Double Asteroid Redirection Test (DART) mission successfully demonstrated this concept by intentionally colliding with Dimorphos, a small asteroid moonlet orbiting the larger asteroid Didymos. The impact changed Dimorphos' orbital period by about 32 minutes, proving that humans can intentionally alter the motion of a celestial object. While the DART mission marked a critical milestone in planetary defense, our hypothetical 10-kilometer asteroid contains billions of times more mass than the 160-meter Dimorphos. Could we scale up this approach to handle such massive objects? We would need either much larger impactors or much longer lead times to gradually shift its trajectory over years or decades. Another promising approach is the gravity tractor concept. This method uses the mutual gravitational attraction between a spacecraft and an asteroid to slowly pull the asteroid into a different orbit. The spacecraft maintains a constant distance using low-thrust engines, providing precise control and avoiding fragmentation risks. However, even a massive gravity tractor spacecraft would need decades to produce a meaningful orbital change for a 10-kilometer asteroid. When facing larger asteroids or shorter warning times, many scientists consider the nuclear option. This approach involves detonating a nuclear explosive device near an asteroid, offering much higher energy density than conventional methods. But how reliable would this be against a cosmic threat? The effectiveness depends heavily on the asteroid's composition and structure. A loosely bound rubble pile asteroid might fragment rather than deflect, potentially creating multiple impact threats. Additionally, international treaties prohibit nuclear weapons in space, complicating both development and deployment. Can the world unite against an asteroid threat? International coordination represents another significant barrier to effective planetary defense. The United Nations has established the International Asteroid Warning Network, IAWN, and the Space Missions Planning Advisory Group, SMPAG, to coordinate global responses. IAWN coordinates asteroid tracking efforts worldwide, while SMPAG focuses on developing collaborative research and mitigation plans. Events like the Planetary Defense Conference bring together scientists, engineers, and emergency managers to improve coordination. However, significant gaps remain in decision-making authority and funding responsibilities. If an incoming asteroid threatened a specific region, who would authorize a deflection mission? Who would fund it? These questions remain largely unanswered at the international level. Funding limitations further constrain our defensive capabilities. Despite the existential risk posed by large asteroid impacts, NASA's entire planetary defense budget represents less than 0.1% of its overall funding. Are we investing enough to ensure our survival? This limited investment slows the development of detection systems and deflection technologies that could prove essential. The situation is gradually improving. NASA's NEO Surveyor mission, scheduled for launch no earlier than September 2027, will enhance asteroid detection capabilities by leveraging infrared technology. The mission aims to discover 90% of near-Earth asteroids 140 meters or larger within a decade of launch, significantly expanding our early warning capacity. Other assets like the James Webb Space Telescope are being repurposed to support planetary defense. In March 2025, it observed asteroid 2024 YR4, which had a small chance of impacting Earth. These observations helped refine assessments of the asteroid's size and trajectory, demonstrating how even general-purpose scientific instruments can contribute to planetary defense. What technologies could prevent an extinction-level asteroid impact like the one that ended the dinosaurs? We have several approaches: kinetic impactors, gravity tractors, and nuclear options. But they all share a critical limitation. They require years of warning time to be effective, especially against larger asteroids. This limitation underscores the importance of early detection. With sufficient warning, ideally decades, even our current technologies could potentially deflect a 10-kilometer asteroid. With years of warning, we might successfully divert smaller but still dangerous asteroids. But with only 24 hours of warning, as in our hypothetical scenario, no current technology could prevent impact. The sobering reality is that planetary defense represents a race against time. Every additional day of warning exponentially increases our chances of successful deflection. This makes investment in better detection systems perhaps the most critical component of planetary defense. We cannot deflect what we cannot see coming. As we contemplate these technological challenges, Earth's previous encounter with a massive asteroid provides crucial lessons on why prevention efforts remain essential for humanity's long-term survival. Lessons from the dinosaurs. 66 million years ago, our planet experienced an impact scenario remarkably similar to the one we've been exploring. The Chicxulub asteroid, nearly identical in size to our hypothetical planet killer at approximately 10 kilometers in diameter, struck what is now Mexico's Yucatan Peninsula. This wasn't merely a historical footnote, it marked the most recent mass extinction event in Earth's history and permanently altered life's evolutionary trajectory. The impact crater itself tells a compelling story. Centered near the town of Chicxulub on the Yucatan coast, the crater measures about 180 kilometers in diameter, roughly the distance from New York City to Philadelphia. Its massive size reflects the extraordinary energy of the impact. Scientists have determined the asteroid struck at an angle of about 60 degrees, coming from the southeast, a trajectory that maximized the environmental damage by ejecting more material into the atmosphere. The timing of this impact precisely coincides with the Cretaceous-Paleogene boundary, a thin layer of sediment found worldwide that marks the dividing line between geological periods. Before this boundary, dinosaur fossils are abundant. Immediately after, they disappear entirely from the fossil record. This perfect temporal alignment provided the first major clue connecting the impact to the mass extinction. The evidence supporting the impact hypothesis extends beyond this correlation. The worldwide layer of iridium found precisely at this boundary serves as compelling evidence. Iridium is extremely rare in Earth's crust, but common in asteroids. The layer contains iridium concentrations up to 300 times above normal background levels. This iridium anomaly was first discovered by physicist Luis Alvarez and his geologist son Walter Alvarez in 1980, providing solid evidence connecting an asteroid impact to the dinosaurs' extinction. Additional geological markers support this conclusion. The boundary layer contains shocked quartz that forms only under extreme impact conditions, and tektites, glass spherules from rock melted during impact. These materials appear precisely at the extinction boundary, further confirming the violent event that occurred. The Chicxulub impact, in our hypothetical scenario, would produce nearly identical initial effects. Both involve asteroids of similar size striking at similar velocities. The Chicxulub asteroid released energy equivalent to roughly 100 trillion tons of TNT, approximately 10 million times more powerful than the largest nuclear weapon ever detonated. The fossil record reveals the devastating consequences. Approximately 75% of all species on Earth disappeared within a geologically brief period following the impact. The extinction affected dinosaurs, marine groups like ammonites and mosasaurs, numerous plant species, flying pterosaurs, and countless smaller organisms across all environments. Evidence suggests that many deaths occur rapidly. In North Dakota, a remarkable fossil site called Tanis preserves fish with impact debris embedded in their gills, suggesting they died within hours of the impact, as ejecta rained down. Plant fossils show a sudden transition from diverse Cretaceous species to a post-impact landscape dominated by ferns, the first plants to recolonize after catastrophic disturbances. Not everything died, however. The survivors reveal important patterns about resilience to asteroid-induced extinction. Small, burrowing animals fared better than larger. Surface-dwelling species. Freshwater ecosystems showed higher survival rates than marine environments. Among the most successful survivors were early mammals, our distant ancestors. These small, primarily nocturnal creatures already possessed adaptations for surviving in darkness and maintaining constant body temperature during environmental fluctuations. Without the asteroid impact, mammals might have remained small, secondary players in dinosaur-dominated ecosystems. Other notable survivors included crocodilians, turtles, and birds, the direct descendants of dinosaurs. Birds represent the only dinosaur lineage that survived, likely owing to their small size, flight capability, and efficient respiratory systems. The recovery timeline following the Chicxulub impact reveals how long Earth takes to heal from such catastrophic wounds. Marine plankton populations began recovering within a few thousand years. Terrestrial plant communities took approximately 10,000 years to regain significant diversity. Full forest recovery required 100,000 to 300,000 years. For animals, especially larger vertebrates, restoring ecological complexity took millions of years. Full ecosystem recovery, measured by the restoration of complex food webs, required approximately 10 million years. This extended time frame emphasizes that while life proves remarkably resilient, recovering from extinction-level events occurs on timescales essentially meaningless to human civilization. The evolutionary consequences of the Chicxulub impact were profound. The asteroid essentially reset Earth's evolutionary trajectory. Had it missed Earth, non-avian dinosaurs would likely have continued their 165 million year dominance. Mammals might never have evolved beyond small, nocturnal insectivores. Primates and ultimately humans might never have evolved at all. This impact represents a significant random event in Earth's biological history, a cosmic accident that redirected evolution toward mammalian dominance, eventually making human existence possible. Our entire civilization exists because an asteroid happened to intersect Earth's orbit at a particular moment 66 million years ago. With this understanding of Earth's impact history, what does our future hold? We exist in a solar system still filled with potential impactors. The same physics that delivered the Chicxulub asteroid remains operational today. Yet, unlike the dinosaurs, we possess something unprecedented: the capacity to detect these objects and potentially prevent impact. Today's planetary defense efforts directly build on the lessons learned from studying the Chicxulub event. By understanding the precise mechanics of past impacts, scientists can better model potential future scenarios. Our tracking systems, deflection technologies, and international cooperation frameworks represent humanity's first attempt to break the cycle of random cosmic catastrophes that have repeatedly shaped Earth's history. This fundamental difference, awareness and technological capability, separates us from all previous species that faced cosmic threats, offering a unique possibility: the prevention of our own extinction. Throughout this exploration of an asteroid impact scenario, we've seen both our vulnerability and our unique capability to prevent extinction. The physical forces unleashed by a 10-kilometer asteroid would transform Earth's systems beyond recognition, yet we possess something the dinosaurs lacked: awareness and technology. Our detection systems and deflection capabilities offer genuine protection against cosmic threats. The DART mission proved we can alter an asteroid's path, a watershed achievement in Earth's history. We stand as Earth's first line of defense in the cosmic storm.